but it's not terribly useful. The main reason it's not useful is because you remember not to write things down, haven't you? That's quite an achievement. You sure you're not writing anything down? You're not secretly writing, are you? On your... No, that's all right. Put your hands up like this, come on. I am not writing. Okay. What you need is to have a box with input U and output Y that's very easy to connect to other boxes, like this. Now, you're cleverer than I am if you can see that it is intuitively obvious, given a system description like that, how you write a formula y equals some function of u. You can easily do it this way. You can get a solution to that, but it's not something that just trips off the tongue easily. There's a lot of slog involved, it's not easy. However, if you have the magic Laplace wand, the LP1, which is yellow because I'm black round the way down the end, white, black at the end, and you wave it over the system, waggle, waggle, waggle. I think what you do, you must have seen this film Frozen, yes? Good. She stamps her foot and the ice pop. You could do the same thing, couldn't you? There could be some lass here. She has her Laplace foot. She stamps her flat. And it transforms this into something like... Did you know that Frozen, with all its merchandising, has increased Disney's profits alone by 22% this year? And they sold as many... This is what happens of getting married again late in life and having a 2-year-old. I mean, a little lass is obsessed with Frozen. You can't take her in a shop without coming out the big hole in your credit card. It's only 2. They sold more dresses, Elsa dresses, than there were 4-year-olds in America. And when you're in the wrong business of doing engineering, get into films and children's animation. The biggest market leakage there is a whining toddler in a supermarket or a toy shop. You'll pay anything to shut them up. It is not good for their personal development, but we've all done it. I'm sure I used to lie on the floor and scream my guts out wanting something. My mother would have hit me or bought it. I think it probably hit me because you weren't allowed to hit people. You were allowed to hit people when they were Anyway, beside the point. Right. So you wave your magic Elsa wand or stamp your foot, and you get something like this miraculously occurring. And that means you can write a simple formula that says y of s is equal to h of s, u of s. That's why we use Laplace transforms. This becomes a simple algebraic equation that you just factor the u and the y out, simple bit of change or something in the formula, and you get that. This looks like Ohm's law. Does anybody remember why it happens and why it looks like that? The L word. What's the L word? Yes, it's because Laplace transform, that's all you've got to say. It's a bit like learners. I mean, I'm totally tempted sometimes to go and take an L plate off a car and put a picture of a Laplace transform on and see what would happen, what the police would do. Anyway. Yes, it's getting big. This is theory. This allows all of the linear stuff. I mean things like loop and nodal analysis, all the stuff you did in circuit theory in the first year electrical course, all to apply. They don't have to be Laplace, they don't have to be capacitors, inductors, resistors, they can be system blocks. You can apply loop and nodal analysis or simple series and parallel formulae, things like this. They're slightly changed because 2 in series don't add up, they multiply. 2 in parallel add, but if you've got those basic differences, all of the rest of the rules apply. So this means you could glue together every electrical transmission cable in the country and every generator and every electric kettle all into a vast network and apply loop and nodal analysis to it. And that's what people do. That's how the CEGB or whatever they are now, central, who are the generating authorities, actually work out how to put fuel into the generators. They do an enormous network model for the whole country. Work out loads and transient effects and all the rest of it. And they use all this sort of stuff. So anyway, that's why you do Laplace. It has a spin-off that you can easily solve the mathematics. If you want to see what's the output, once it's in this form, all you have to do is to wave your... Well, what would she do? Suppose you'd have to lift her leg up, wouldn't she, and kick that way. That's the opposite to freezing. No, no, I know what she says. What was it? An act of love, wasn't it? Generosity caused all the ice to melt. So that's your inverse transform. So remember Elsa in Frozen, she stamps her foot to do a forward transform and says love and it inverts. It would be nice if it was that easy to do in an exam. You could be sitting there all going bang. This is a sort of aid to memory. You'd be surprised how it helps you to remember things. So all you do is you wave your magic wand or get Elsa to stamp her foot on this, and you end up with y of t equals something. It depends on the input. So you can use it as a method for solving differential equations as well. I mean, don't forget, if there are initial conditions here, we got an extra few terms, but they don't really change things very much. So Laplace transforms are the ideal tool for A, marketing Disney products, and B, doing manipulation of systems. I'll give you a simple example of a system block diagram. These things have got H1 here, H2, there's one there, H3, add them up, U. So what's that's equivalent to a single system with U, and I'll call it big Y again. Big U and big Y coming out, H total of S, and it should be easy to see that H total of S is simply equal to that one times that one. It's that simple. You just write this stuff straight down. So doing what's called block diagram algebra is very simple using the Laplace techniques. Right, now, this object H, which is the thing that looks like resistance in this form, is called the transfer function. Remember, we have initial conditions are always set to 0 for transfer functions. This is the thing we're interested in, and that tells us what the system's like. So let's take our two simple examples here. First one is as a we do the Laplace stuff, we get sy of s plus 3y equals u, which leads to the transfer function h is equal to what? Rubbish. 3. 1 upon s plus 3. And the second one is s squared y plus sy plus 10y equals u plus 2su, and that leads us to 1 plus 2s over s squared plus s plus 10. And these are the two transfer functions for this system. It should be fairly clear that given stuff on this side and stuff on this side that looks generally like this, and all the systems that you're going to deal with will, you always end up with a load of factors in S on the top and factors on the bottom. So the transfer function is basically a ratio. H is a ratio of polynomials in S. Now, it turns out that it's the bottom, the denominator, that characterises the polynomial. And I would choose that one, wouldn't I? So I think we're going to change this. I'll have 3, 2, and I'll have 3 and 2 here because I can't be bothered to factorise the other one. So if we write this one like this, I'm going to take the half outside this one. So if we write that thing like this, it turns out that it's the denominator, thing on the bottom, that tells you what it's about, fundamentally what the system does. This is because we can split it into two factors using partial fractions, and you can do that bit yourself, where A and B are constants. So we can turn this second order system, or if there were three, we could, if it was a cubic system, third order, we could turn it into three terms. You can always turn it into the sum of a collection of these things which are first order systems. And the first order system is defined in terms of its dynamics by these quantities that are called the poles. The bits on top, in this case here, more sensibly, are called the zeros. They add detail, but they're not critical for the dynamics. And we plot the description of our system in the S-plane. The poles are identified typically by crosses. So this system would have a pole at -1, pole at -2, and it would have a 0 at -0.5. The zeros are dots. Okay? This is the J times the imaginary number of the pole, and this is the real number. No writing. There's a switch on the side, just turn it to store data. You can also plug into the socket on the other side and download it. You've all got a USB implant, it came with your laptop. Yeah. Right, so it's the poles that determine really what the system does. You can always make a high order system out of a set of first order systems like that. Now that's interesting because that means a box like this, which is that box, is equivalent to a whole load of boxes like this all stacked in a line. So it immediately gives you an alternative way of building complicated systems from simple ones. Or if you want, if this were third order, you could make one second order system and one first order one. I mean, it gives you all sorts of games you can play with networks and with system synthesis. But we have an S-plane which describes our systems. You can put 2 down if you want here, because that means the whole thing is times by 2, because we have a factor 2. That's sometimes called the gain of the system. It's just an overall scaling factor. So these S-plane descriptions completely describe our system. Am I going too fast? Do you want me to slow down? Is this all right? Please interrupt at any time when you want to ask any questions. Any questions? Yeah?
If the poles were complex, would they go up onto the...
Yes, they would. That's the next thing I'm going to go through. What the different systems do. Okay? So let's start with various systems. Simple one, first order one dy dt plus y equals u. H of s is 1 over s plus 1. The S-plane is just there at -1. That's first order, one pole, it's on the real axis, and if you do the solution to this differential equation, it's basically a soggy, this is y, t, and that's t. It's a soggy decay, no oscillations. The second type of system is going to be second order, what we just did. I won't bother with a 0, I'll just put it equal to no zeros. That one has, again, -1 and -2 poles. We've just seen you can write it as the sum of